Morning guys, this is a continuation of our lecture on plate stability analysis. So for the buckling of uniformly compressed plate, we consider a plate element with dimensions A and B as shown, wherein the length A is actually the side upon which the force inducing buckling is applied, which is labeled here as Nx, equivalent to the critical buckling stress multiplied by its thickness, while B is the dimension perpendicular to the length A. So if we now consider the plate to have buckled considerably as shown here in the figure, so just to magnify the angle upon which the curvature is based on. So we take note that the forces Nx at the initial end is actually magnified by simply adding again an equivalent delta Nx here, which is simply defined as the partial derivative of your Nx with respect to x dx. So with the angle or the slope, since we are talking here of a differential length dx only, so your slope here will simply be equivalent to a delta omega or w plus a delta w. Okay, so since your slope is defined in terms of the partial derivative of w with respect to x, so your final slope here will simply be equal to the partial derivative of w all over x plus a delta of delta w. Okay, so it's just like saying that the slope theta at this side is simply theta plus delta theta. Now, since it's already an increment delta theta, we can now make use of delta theta as your parameter to represent your slope or angle at the far end side. So the governing PD for plate element derived above was actually expressed in this manner. So this was previously derived in the last video, where Q is defined to be this value here. And I'd like to take note that this has something to do with the moment, okay, M. Remember that omega here or W is not a load, but it is a deflection brought about by the buckling effect. And since M over EI is simply a measure, okay, so it's a measure of your curvature, so this is unitless, it's dimensionless, such that your Q is actually induced by an axial force rather than a transverse load. So the only difference with this plate buckling is that your load is no longer a transverse load, but it is an actual load. So to show you a proof on this, we consider the forces along the z direction. Okay, so the z direction is actually the vertical direction summation, no? In which your nx and your value here for nx plus delta nx is simply a sum, okay, vertically, such that if we are going now to count the number of forces, it's simply the component of this, okay, nx, and the component of this nx plus delta nx. Of course, the angle here are not the same, so we have to multiply it by the slope or simply the tangent of the angle to come up with this equation here. Aside from those two forces, of course, we have to equate it on the load applied uh, transversely. If there is a load, transverse load Q on your plate element. Actually, this transverse load Q will then be the basis for our consideration for the actual load nx later. Okay, so this is now your vertical downward force, and this is the upward force multiplied by the, of course, the corresponding slope. So this is the corresponding slope, which is simply a derivative, no? And this is also a derivative corresponding to the slope. Okay. So if we now distribute this value here with this slope here, we will come up with 4 expressions. But since this is actually the negative of this part here, so if I distribute this part here, and this happens to be okay, so these are the slope, and this here is simply the negative of this value, so it simply cancels out. Okay, so these values, these two values here cancels out. So what remains are still 3 or 4 expressions, including of course your q dx dy. Okay, so this is multiplied now to this one, which is this, and then this is multiplied to this one, which is this derivative here. Okay, so it's also negative, and and this will also come up with a triple sorry, yes, a third degree differentiation, which is a third order derivative, this one here, still negative. Okay, so all of these now are negatives, and this is positive, and we try to eliminate those values which are not meaningful to us by simply neglecting higher order infinitesimals, this second terms here, and third term, second and third term will then be assumed to vanish. Okay, so this is a third degree derivative, and this is also a second degree derivative here of a slope. So it becomes a smaller and smaller, such that your remaining equation will only be this here and this q here. Okay, so q is simply equal to the negative of nx d squared over dx squared of your wxy. So this, in the book, this is actually written as negative nx all over d partial derivative of second partial derivative of omega all over with respect to x squared. So the reason why I write it down like this, because MathCAD cannot write it this way, is partial derivative. But take note that when you are using a derivative sign, we have to see to it that we put the parameters, the independent variable, as parameters for your differentiation, in order to emphasize that this has actually two independent variable concerned. So this will bring us into this equation now, such that your q was replaced simply by, okay, this value here. Okay, so this is just a proof that q is actually the same as this value here. Now, to solve this differential equation, we use the method of separation of variables as a tool to come up with a solution. No? So this is a two-dimensional equation. So two-dimensional partial differential equation. So the solution is actually done by first separating the variables. We simply apply the solution, this assumed solution, into the governing PDE. Okay, so this is now the assumed solution, and the assumed solution is simply the product of the individual solution for the x variable and the y variable. Okay, so what we are going to do now is to substitute the derivative of this solution into the governing differential equation. And by using symbolic operators of derivatives in the form of prime, double prime, triple prime, and quadruple prime, we simply state that we're taking the order of the derivative, taking note of how many times we put the symbol prime into the variable itself. So if I take the fourth derivative of this solution, I just make use of the derivative of x 4 times, no, multiplied by y, assuming that y is a constant. So that's how you use a partial differential equation procedure. So you assume the the other variable to be constant, and then take the derivative of the first variable. So this is x quadruple prime y, and then plus, again, we take the partial derivative of this solution twice with respect to x and twice with respect to y. Okay, so we now assume first y to be constant, so this becomes 2x double prime, and assuming y, or sorry, x to be constant, we take y double prime. And so is true with the third one. We take the fourth derivative of this solution, assumed solution with respect to y, by taking now your x to be your constant. So we get now your value x y quadruple prime is equal to a real constant minus nx over d. This is the second derivative with respect to x, so x double prime y. Okay, and the next step is to assume again a solution of the ordinary differential equation in the form of the x variable. No? So we assume now a simple sinusoidal solution. So this is a sine wave to capture a solution that will represent your x a variable here. So this is a sine wave or a sine graph, sinusoidal wave solution in the form sine of an angle, okay, wherein this angle here represents your eigenvalues in the form m pi x over a. So we did this last time when we derived. Okay, so remember when we derived the Euler buckling load. Okay, so we note that the eigenvalue function, or sorry, the eigenfunction is in the form of a sinusoidal function equivalent to sine of n pi x over L, okay, such that this represents values equivalent to the angle P. I think this is P over EI. Okay, so this is now the angle P over EI, or something like the square root. Okay, so this is square root of P over EI to come up with this solution here. So it's just the same. Here we have the n pi x or n pi y, I think, over L. Here it's an m pi x over A. So note that the solution of this x of x satisfy a zero deflection and a zero moment. Okay, so this is a zero moment at the boundaries for simply supported end condition, and substituting this gives this value here. Okay, so we simply substitute the fourth derivative of this, which is, if I differentiate sine 4 times, I get sine, cosine, sine, cosine, sine. So I get a sine back and then multiply it 4 times with this m pi over a to the fourth. Okay, and so it's true with this. We have 2 times m pi over a squared sine. The derivative of sine twice is also sine. If you differentiate sine 2 times, it will give you the sine uh, function again, but you have to multiply it by the coefficient m pi over a squared. And so is true with the rest of the expression. So the term sine m pi x over a can now be cancelled here. Okay, so you can cancel it here. Obviously, each and every expression have this in the formula. So by cancellation, we reduce the equation into this one, and okay, arranging your equation into an ordinary differential equation in y. So this is now an ordinary differential equation in y. Okay, so you have 4 to the fourth derivative, to the second derivative, 0th derivative. So we can make use of a characteristic equation or auxiliary equation to come up with the solution of this. So this is just a quadratic equation in the form r to the fourth minus 2 quantity m pi over a squared. Sorry, it's r to the fourth minus 2 quantity m pi over a squared r squared plus this, which is a constant of your variable y. So we actually convert this auxiliary variable r, or sorry, convert y into an auxiliary variable r, and then assume that the order of the derivative is your exponent. So this becomes 4, this becomes 2, and this becomes 0. So any number raised to 0 is 1. Okay, so this is now my equation, and this is simply a quadratic equation in this form. So I can make it in this form, and take note that here my a is equivalent to 1 because I don't have any coefficient in this. Okay, so my coefficient here is a equals 1, and my b is simply this one, and my c is simply this one. Okay, so my a is 1, my b is this, but my b over 2 is simply divided by 2, I get this, and my c is this one here. Okay, so this this is my b, this is my b, and this is my c. And take note that my root of r to the fourth is r squared, the first square root. So we yield to this value here. And finally, if I take again the square root of this, I will be yielding to 4 roots which are distinct. 2 are actually distinct, and they are simply this one here. These are distinct roots in the sense that you have a possible real, okay, real root here and a possible complex root here. Okay, because of that negative sign, a possibility of having, and this is simply a plus or minus value there, and this is a plus or minus value. So if I have 4 roots, I will be getting into a solution which has 4 terms and 4 coefficients yet to be determined. So since I have here real roots, my form of solution must be maybe hyperbolic or exponential, no? So it can be also placed in an exponential form. And here I will get a trigonometric or uh, an exponential also, no? Remember that the trigonometric part will capture the complex root, and the hyperbolic part will capture the real root. So this is now my hyperbolic sine and cosine and trigonometric sine and cosine, which has, of course, coefficients yet to be determined by applying the boundary condition. And in totality, the final solution will simply be the product of my solution for x and y. So I simply multiply the x solution a while ago and the y solution here. Okay, so this is now a very complex solution wherein uh, we can make this simpler by way of eliminating those possibilities that won't help us capture the behavior we are trying to get. Okay, so first, if we take a look at this sine and cosine hyperbolic function, we take note that the sine hyperbolic function has a graph, a graph more or less uh, in this okay. So this is my sine hx and my sine hy or cosine uh, hy. So this is not x, no? So this is y. Of course, here there's an alpha and a beta there, no? So we assume we neglect first those coefficient, but the form of the graph will still be the same. So the cosine will have somewhat like this as your graph, no? So if you are going to take a look at this equation here, so there will be a case, a scenario wherein the value of sine, hyperbolic sine, will lead to a zero value there that will not contribute to the effect of the behavior of what we are trying to get here. While the cosine hyperbolic will always get a value whether you have C2 as 0 or not. Okay, a non-zero C2 will give you a value at any point, okay, along uh, this curve here, which means to say, class, that C1 or this value here rather can be eliminated by setting this coefficient to be 0. Okay, uh, in simple language, C1 and C3 may be eliminated simply because it will yield to some result that will not be contributory to what we are trying to get later. Of course, you can also do it in C2 and C4, but in this case, if you do that, you will no longer have a solution. So to make the total solution or final solution non-trivial, we must assume, we must force that C2 and C4 must not be equivalent to 0. Okay? And let your cosine hyperbolic and cosine trigonometric give you the behavior you are expecting to get. And of course, we're now talking of the boundaries on your y. So this is your x-axis, and this is your y-axis. So the boundaries on the y, if this is 0, will start at negative b over 2 and b over 2 if this is your width b and length a. Okay? So using support conditions at y b over 2 and negative b over 2 requires that the value y, the deflection, the moment values are there, of course, to be 0. That is, the deflection is equal to 0 is equal to the sine of m pi x over a. We simply substitute b over 2 here, okay, and b over 2 we can do it one at a time, of course. Okay. Take a look at the cosine of a negative angle and the cosine of a positive angle are simply the same but only different in sign. Okay. So if I substitute here, the deflection will only be on the other side. Okay, so that's what will happen if we use a negative b over 2 instead. So taking also the derivative of this value here with respect to y, so this is now a constant. So since this is with respect to y, this becomes an x variable, so this is a constant. We don't have to worry about it. So this now becomes the second derivative of a hyperbolic cosine and a trigonometric cosine are just the same. But of course you have to multiply it by the coefficient of the angle alpha twice. Okay, so alpha squared and beta squared will come in this equation. So for a solution other than C2 equals C4 equals 0, of course, it's necessary that the determinants of these two must be non-zero. No? So to make an equation non-trivial, the solution, or sorry, the equation must not be singular, meaning to say the value of the determinant must not vanish in order for it to have a solution. Okay, so this is now my determinant. If I will make this as a matrix, no, I can plug in the value. Of course, this is just a coefficient, so this is now my coefficient of C2 is simply this. So I will write cos alpha b over 2, and then beta b. Okay, beta b over 2. Okay, and this one here will be alpha squared cos of alpha b over 2 and beta squared cos of beta b over 2. Okay, so this is now my matrix, and then of course this is your C2, C4. So if I want to get the determinant of this, I simply make use of an upper multiplication plus, okay, something like this. And if I multiply this and this, I will yield simply this solution here. And for this again, not to be trivial, or to make this non-trivial, the determinant of this must be 0. And this is the determinant. So this is now the value of the determinant of this matrix. Okay. And take note that for this non-trivial solution also to be valid, this part here must be 0. So this must be equated to 0. Alpha beta squared must not be 0, because if alpha and beta are 0, then there's no behavior that is going to happen. Okay, a buckling behavior that is going to happen. So if we set now this to be 0 and this to be non-zero, we can solve for the angles such that my angle now of beta b over 2 must be multiples of pi over 2. So pi over 2, 3 pi over 2, uh, 5 pi over 2, etc. Okay, so these are now actually add multiples of pi over 2. And of course, for a critical value, you use always the lowest value, pi over 2, and equating the value of beta, we have okay, if we equate now the value of beta here, we get this equation. We solve for beta simply to be equivalent to pi over b. And this pi over b now is simply this equation here as defined in your solution a while ago, this complex solution here. Okay, so we can now link this here for us to be able to get our value of nx by simply cross multiplying. So this becomes d pi squared over b squared. So we recall in our figure above that nx is simply the critical boxing stress multiplied by t, and d is simply equal to bh cubed over 12. No? So this is just ei all over 1 over nu squared. Okay, so this is just the flexural rigidity. And if we define this k to be a over mb plus mb over a quantity squared, then your FCR now will simply be equivalent to k pi squared e divided by this one here. So it's just a way of substituting your nx here and then solve for, and putting this as your k value and putting d there, okay, and solve for FCR. So this is our final basis or final equation that will serve as basis for local plate buckling. So take note that the integer m indicates the number of half waves that occur in the x direction, which means that if I have here a plate with an A over B ratio or the aspect ratio. So the number of half waves 1, 2, 3, 4 will determine M. Okay? So the weakest situation occurs when the length is an even multiple of the width and that the multiple is equal to the number of half waves. Okay? So what is M? Okay, M is A over B. So when this is an even multiple or even number, then it is in the weakest. So different values of K will arise, and this was found on tests, of course, that these values are based on end conditions. And the end conditions refer to these edges here, okay? So if this is fixed and this is free, then your buckling maker like this. So for a fixed we have this, the fixed simply supported we have this, the simply supported we have this, the fixed free we have this, and for the simply supported free we have this. Okay, so for the most critical, of course, we have the simply supported free. For the most shall I say conservative, we have this the fixed scenario. So we can rewrite the equation now above in the form B over T. Okay, so we are referring the equation here. Okay, so we can make use of a width to thickness limit or slenderness limit instead of, okay, so this is the slenderness normally given by the lambda, okay, slenderness limit. So is now derived using the formula for the local buckling stress considering stability of plates is concerned. And to ensure that Fy is achieved first prior to local buckling, we simply substitute or insert the value of Fy to get the limit. Okay, so we are now taking the limit of lambda, which is B over T, equivalent to 5,120 square root of K over Fy. Of course, this is in English. By substituting E equals 29,000 PSI or KSI and nu is equal to 0.30. Of course, we have to substitute PSI here because your FYR are normally based on PSI. So to account for residual stress, we reduce this value to 0.70, so we get 3580, and this serves as the basis for your LRFD B5.1 and ASD B5.1 equation, such that the theory of bending of plates and elastic stability considers not only the possibility of buckling of the member based on slenderness ratio, but also considers local buckling which may occur first in one of the elements that make up the section, and to consider the elastic buckling stress given by this formula. We take note that K is the elastic plate bending coefficient, nu is the Poisson's ratio, and K is simply this value here in the parentheses. If I set my M, my multiple number of half waves to be A over B, then exactly my K is equal to 4, which refers to the simply supported, because this will just come up with a value A, then A over B times B plus M, plus A over B times B over A. Okay, so squared, so you get 1 there, 1 here, 1 plus 1 becomes 2 squared, so this is 4. Okay, again, using E equals 29 million and nu as 0.30, Poisson's ratio of steel, which can still increase, no, depending upon the ductility of the material. No? So this becomes now 2.621 times 10 to the 7 K all over B over T squared. So note, K depends on the type of stress. If it is shear stress, bending stress, axial stress, compression, etc. Support condition, if it is fixed, free, simply supported. Aspect ratio, A over B ratio of the plate. So let us now define lambda sub C squared on this basis. We all know that lambda sub C squared is simply Fy over F Euler, or F critical rather, because this is now based on the plate stability, okay, analysis. So we substitute this there and we get this equation in PSI and this equation in megapascal. And these are again the basis for the limiting width to thickness ratio, LR or lambda R, okay, lambda R, to achieve yield stress without local buckling. So if you hear the compact and non-compact section now, so this is what we are deriving at in this video lecture. Okay, thank you very much. I hope you have been informed of how plate elements behave in terms of stability by the application of actual loads, and I'll see you on the next video for the continuation of such application on torsion and lateral torsional buckling. Thank you very much.